Chemical formulae are the language of chemistry, using symbols to represent elements and numbers to show the proportions of each element in a compound. Stoichiometry is the quantitative study of the relationships between the amounts of reactants and products in a chemical reaction. The mole is the fundamental unit in chemistry, representing Avogadro's number 6.022 times 10 to the power of 23 of particles, whether atoms, molecules, or ions. Understanding formulae, stoichiometry, and the mole concept is essential for quantifying and predicting the outcomes of chemical processes. In this section, we'll explore these core principles and how they underpin our understanding of the chemical world. Chemical formulas provide a concise way to represent the molecular structure and atomic composition of a compound. They show the types and numbers of atoms present, indicating the specific elements that make up the compound. The formula uses chemical symbols to represent the individual elements in the compound. Understanding chemical formulas is crucial for studying the properties and behavior of different substances. Formulas allow us to communicate the composition of a compound in a clear and standardized way. Chemical formulas use symbols and numbers to represent the composition of a compound. They provide a concise way to communicate the identity and structure of a substance. Compounds can be formed through ionic bonds between metals and nonmetals or covalent bonds between nonmetals. The type of bonding determines the compound's physical and chemical properties. The arrangement of atoms in a compound is its molecular structure, which can be visualized using models. Molecular structure provides important insight into a compound's geometry and reactivity. Molecular formulas provide the exact number and type of atoms in a molecule, showing the true composition of a compound. Empirical formulas show the simplest whole number ratio of atoms in a compound, representing the basic composition without indicating the actual molecular structure. Molecular formulas are more specific and detailed, while empirical formulas are simpler and focus on the basic elemental makeup. Understanding the difference between these two types of chemical formulas is important for accurately representing and understanding the composition of compounds. The goal of balancing chemical equations is to ensure the number of atoms of each element is the same on both the reactant and product sides. The first step is to identify the reactants and products involved in the reaction. Next, we'll count the number of atoms of each element on both sides to make sure they're equal. If they're not equal, we'll adjust the coefficients of the reactants and products until the number of atoms balances out. Balancing equations is a crucial skill in chemistry, as it allows us to accurately represent chemical reactions and understand the underlying processes. Stoichiometry is the study of the quantitative relationships between the amounts of reactants and products in a chemical reaction. There are three key relationships we'll explore: mole-mole, mole mass, and mole volume. The mole-mole relationship looks at how the number of moles of reactants and products are related. The mole-mass relationship connects the number of moles of a substance to its mass. The mole-volume relationship allows us to determine the volume of a gas based on the number of moles. Understanding these relationships is crucial for predicting and calculating the amounts of substances involved in a chemical reaction. We'll dive deeper into each of these three relationships in the upcoming slides. This slide introduces the topic of mole-mole stoichiometry, which is the study of the quantitative relationships between the amounts of reactants and products in a balanced chemical equation. It outlines the key steps involved. Start with a balanced chemical equation that shows the mole relationships between the reactants and products. Identify the mole ratios between the different substances in the balanced equation. Use these mole ratios to determine the number of moles of one substance given the number of moles of another substance. These mole-mole calculations are essential for understanding and predicting the outcomes of chemical reactions. The visual of the scientific glassware helps reinforce the laboratory setting and experimental nature of this topic. The key steps in mole mass stoichiometry are: start with a balanced chemical equation to represent the reaction. Determine the molar masses of the reactants and products. Use the balanced equation and molar masses to calculate moles of reactants and products. Convert between moles and mass using the molar masses. This allows us to predict how much of each substance will be produced or consumed in a chemical reaction. Mole mass stoichiometry is a powerful tool for understanding the quantitative relationships in chemical processes. The key relationship we're exploring here is the connection between the number of moles of a gas and its volume. Avogadro's law tells us that the volume of a gas is directly proportional to the number of moles. The more moles, the greater the volume. At standard temperature and pressure, 0 degrees Celsius, 1 atm, the molar volume of any gas is 22.4 L/mol. This is a useful conversion factor. We can use this molar volume to calculate the volume of a gas given the number of moles, or vice versa. However, for real gases at different temperatures and pressures, the molar volume may differ from this standard value. We need to account for these conditions. The key concepts we'll cover in this slide are limiting reactants, excess reactants, and percent yield. The limiting reactant is the one that is completely used up in the reaction, determining the maximum amount of product that can form. The excess reactant is present in greater quantity than required by the stoichiometry and remains after the reaction is complete. Percent yield is the ratio of the actual amount of product obtained to the theoretical maximum, expressed as a percentage. Factors like side reactions, reaction conditions, and experimental efficiency can impact the percent yield. Understanding these concepts is crucial for predicting reaction outcomes and optimizing chemical processes. The mole is a fundamental unit of measurement in chemistry, just like grams measure mass or liters measure volume. 1 mole represents Avogadro's number, which is approximately 6.022 times 10 to the power of 23 particles, whether atoms, molecules, or ions. The molar mass of a substance, measured in grams per mole, allows us to easily convert between the number of moles and the mass of a substance. Understanding the mole concept is essential for stoichiometric calculations, balancing chemical equations, and analyzing the quantities of reactants and products in chemical reactions. This slide provides an overview of the key aspects of the mole concept and its importance in chemistry. Avogadro's number is a fundamental constant in chemistry, representing the number of particles, atoms, molecules, or ions in 1 mole of a substance. This crucial value allows us to connect the microscopic world of atoms and molecules to the macroscopic quantities we measure in the lab. Avogadro's number is 6.022 times 10 to the power of 23 particles per mole. The definition of a mole is the number of particles in 1 mole of any substance. Knowing Avogadro's number enables us to make conversions between moles, mass, and number of particles. Molar mass is the mass of 1 mole of a substance, expressed in grams. 1 mole contains Avogadro's number of particles, 6.02 times 10 to the power of 23 atoms, molecules, or ions. Molar mass is an important factor in calculating the cost per mole of a substance. Molar mass allows us to convert between the number of moles, mass, and number of particles of a chemical compound. Understanding molar mass is fundamental to working with chemical quantities and stoichiometry. The key concepts on this slide are the 3 main conversions between moles, mass, and number of particles. To convert moles to mass, we multiply the number of moles by the molar mass in grams per mole. To convert mass to moles, we divide the mass in grams by the molar mass in grams per mole. To convert moles to the number of particles, atoms, or molecules, we multiply the number of moles by Avogadro's number, which is 6.022 times 10 to the power of 23 particles per mole. These 3 conversions are fundamental in chemistry and allow us to move between different units when working with chemical quantities. I'll walk through some examples of each conversion to make sure the audience understands how to apply these formulas. The title of this slide is Mole Calculations with Compounds. It introduces the key concepts we'll be covering. Molecular formula, the actual arrangement of atoms in a molecule. Molar mass, the mass of 1 mole of a substance. Mole mass conversion, calculating mass from moles or moles from mass. Understanding these concepts is crucial for performing stoichiometric calculations and analyzing chemical reactions. We'll dive deeper into each of these topics in the upcoming slides. Mole calculations with gases involve relating the moles of a gas to its volume using the molar volume. The molar volume is the volume occupied by 1 mole of any ideal gas at standard temperature and pressure, STP, conditions. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. Understanding these key concepts will allow us to perform calculations involving the relationship between moles and volume of gases. The molar volume of a gas is the volume occupied by 1 mole of the gas at a given temperature and pressure. At 0 degrees Celsius, the molar volume is 22.41 L/mol. As the temperature increases to 20 degrees Celsius, 40 degrees Celsius, 60 degrees Celsius, and 80 degrees Celsius, the molar volume increases to 24.79 L/mol, 27.18 L/mol, 29.57 L/mol, and 31.96 L/mol respectively. Density is a fundamental property that can be used to identify and distinguish different materials. Density is the mass per unit volume of a substance. It's an important characteristic that helps us understand the physical properties of materials. Molar mass is another key property. It's the mass of 1 mole of a substance, measured in grams per mole, g/mol. Molar mass is a fundamental characteristic of chemical compounds. We can use density calculations to determine the mass, volume, and number of particles in a substance. Relating mass, moles, and number of particles is crucial for understanding chemical processes. The images on this slide illustrate the key concepts of measuring density, understanding molar mass, and performing density calculations. These are all important tools for characterizing and working with different materials. Molarity is a way to measure the concentration of a solution. It tells us the number of moles of solute, the dissolved substance, per liter of solution. This is an important concept for understanding chemical reactions, reaction rates, and the behavior of solutions. Molarity gives us a standardized way to quantify the amount of a substance in a given volume of solution. This slide shows examples of different molarity values, 1 m, 0.1 m, and 5 m. It also notes that the measurements are taken at room temperature, 25 degrees Celsius. The key points are that molarity allows us to precisely measure and compare solution concentrations. Dilution is the process of adding solvent to a solution to decrease the concentration of the solute. The dilution factor is the ratio of the final volume to the initial volume. As the volume increases, the concentration decreases proportionally. Concentration is inversely proportional to volume. When volume goes up, concentration goes down. This slide provides an overview of the key concepts related to dilution of solutions. The goal of titration is to determine the unknown concentration of an analyte solution. To do this, we first prepare solutions of the analyte and a titrant of known concentration. We add a small amount of an acid-base indicator to the analyte solution to track the progress of the titration. We then slowly add the titrant solution to the analyte until the indicator changes color, signaling the end point of the reaction. Finally, we use the volumes and known concentration of the titrant to calculate the unknown concentration of the analyte. Chemical compounds can be classified into 2 main types, ionic and covalent. Ionic compounds form when a metal transfers electrons to a nonmetal, creating a positively charged cation and a negatively charged anion. These oppositely charged ions are held together by strong electrostatic forces. Covalent compounds form when nonmetal atoms share electrons, creating stable molecules with no overall charge. The strength of the covalent bonds determines the properties of the compound. Covalent bonds can be either polar or nonpolar, depending on the electronegativity difference between the atoms. Polar bonds have an unequal sharing of electrons, while nonpolar bonds have an equal sharing. Ionic compounds are formed when metals donate electrons to nonmetals, creating positively and negatively charged ions that are attracted to each other. Covalent compounds are formed when nonmetals share electrons, creating stable molecules held together by strong, directional bonds. The ability of an atom to attract shared electrons, known as electronegativity, determines whether a bond will be ionic or covalent in nature. Ionic and covalent bonds have different properties and characteristics that affect the behavior and structure of chemical compounds. Understanding the differences between these 2 types of chemical bonds is crucial for predicting and explaining the behavior of various substances. Polyatomic ions are molecules that carry an overall electric charge, formed by covalently bonded atoms. Common examples include the ammonium ion, NH4+, the carbonate ion, CO3-2, and the sulfate ion, so 4-2. These polyatomic ions form ionic bonds with other ions to create electrically neutral compounds. Polyatomic ions are typically named by identifying the central atom followed by the ate or ite suffix. The molecular structures of these polyatomic ions are visually represented by the colorful models shown in the image. Ionic compounds are made up of a cation, positively charged ion, and an anion, negatively charged ion. When writing ionic compounds, we list the cation first, followed by the anion. To name ionic compounds, we combine the name of the metal and the name of the anion. Covalent compounds are made up of atoms that share electrons. When writing covalent compounds, we list the elements in order from left to right, with the less electronegative element first. To name covalent compounds, we add prefixes to indicate the number of atoms of each element. Polyatomic ions are charged groups of atoms that behave as a single unit. When writing and naming compounds with polyatomic ions, we treat the polyatomic ion as a single unit. The charge of the polyatomic ion is included in the name of the compound. Acids, bases, and neutral compounds are three main types of chemical compounds. Acids release hydrogen ions, H+, when dissolved in water, lowering the pH and giving a sour taste. Bases accept hydrogen ions, H+, in water, increasing the pH and resulting in a bitter, soapy taste. Neutral compounds do not release or accept hydrogen ions, maintaining a neutral pH of 7 and being tasteless and odorless. Understanding the properties of these three compound types is important in chemistry, biology, and many other scientific fields. Acid-base reactions involve the transfer of protons, or H+ ions, between an acid and a base. This results in the formation of a salt and water. The pH scale measures the acidity or basicity of a solution, ranging from 0 to 14. A pH of 7 is considered neutral. Neutralization occurs when an acid and base react to form a salt and water, resulting in a neutral pH of 7. Oxidation is the loss of electrons by a reactant, resulting in an increase in its oxidation state. Reduction is the gain of electrons by a reactant, resulting in a decrease in its oxidation state. Oxidation and reduction always occur together, with one substance being oxidized and another reduced. Balancing redox reactions involves adjusting the coefficients of the oxidized and reduced species to ensure the overall reaction is balanced. These fundamental concepts of oxidation and reduction are crucial for understanding many chemical processes, from combustion to energy production. Electrochemical cells are devices that convert chemical energy into electrical energy. They consist of an anode, cathode, and electrolyte solution. Voltaic cells, or galvanic cells, are a type of electrochemical cell that uses spontaneous redox reaction to generate an electrical current. In a voltaic cell, the anode undergoes oxidation while the cathode undergoes reduction, resulting in the flow of electrons and an electrical current. The electrochemical series, or activity series, ranks elements based on their reactivity and tendency to lose or gain electrons. The key takeaways from this presentation are the fundamental concepts that underpin chemistry: chemical formulae, ionic and covalent bonding, the mole concept, and stoichiometry. Understanding these core principles is essential for mastering chemistry, both in academic settings and real-world applications. Chemical formulae provide a concise way to represent the composition of compounds, which is crucial for understanding their properties and behavior. Exploring ionic and covalent bonding mechanisms helps explain how atoms interact to form stable compounds. The mole concept and stoichiometric calculations enable quantitative analysis of chemical reactions, allowing us to predict and measure the quantities of reactants and products. These foundational concepts have wide-ranging applications, from academic study to industrial processes and everyday phenomena. Mastering these core ideas lays the groundwork for deeper exploration and understanding of the chemical world around us.